Hi, this is the second part of the B tree. I'll show you the source code on my own implementation of B tree using C#. So the link of the source code is in the video description. So in the source code, there are actually 4 CS files. For this one is about the node type, and this one is a basic type for key value pairs of B tree. And this is a simple type of B tree. It's just a collection of comparables. And this one, B tree base, is the real implementation. Let's start from the B tree node. So this one, this is the base type of the node. It contains an array of comparables. This serves as the indexes. And it has a length. Initially it's 0 because in the beginning it's empty, nothing stores in the array. And it has a pointer to its predecessor and a pointer to its successor. It also has a pointer to its parent. And here is also important, it maintains its index in the parent. And then this is the constructor, so the max is the capacity. So when you instantiate this node, you create an array to store the indexes. And this is the index node. This index node inherits the base node. It has one array in addition, which is an array of pointers to its children. So this is the index. This is the index node. And for the leaf node, it also inherits the base node. It doesn't have an array of its children, so because it's leaf node. But it stores the value, stores the real data. So it has an array of the data it stores. So this is a type of the tree node. And here are 2 types of B tree, and this is a simple type. It's a collection of comparables. And this one is key value pairs. It stores key value pairs. But the key is comparable, of course. Value doesn't have to be. The real implementation is the B tree base. Let's see, it has a const list of 2. This means the minimum, the minimum is at least 2. I'll explain to you why that's the case. And it contains a sentinel. I think I explained how sentinel works in the previous video. And it has a minimum. Except it's a the root node, it must contain minimum number of elements, and max is the capacity. And here is the cutoff for borrow and merge. Is useful for the in deletion, whether you borrow or you borrow from its sibling nodes, or you merge into or merge from its sibling nodes. And this is half. Half is when you split the node during insertion. So this is useful. And it stores a pointer of the head. The head it's B tree, the linked list. So this pointer is the head node of the linked list in the leaf level, and the tail is the pointer to the tail node of the leaf of the linked list in the leaf level. And this is the root. So when you do search, you start from the root. Not only search, but insertion, deletion, you also start from the root, and you go all the way to the leaf. So you also have 2 pointers of inserted and deleted. So if you have experience in database, they are useful for database triggers when you do insertion, update, or deletion. So, for example, in Microsoft SQL Server, they're called deleted and inserted Uh, it's called new and old in Oracle or Postgres. So let's go to the constructor. So the constructor, you pass in an integer, and that specifies the minimum. And you also specify it's a simple type or it's a key value pairs. Simple B tree is a collection of comparables. If it's not simple type, then it's key value pairs. Simple tree is a collection of comparables. And here minimum is the passed in minimum, or it's 2, at least 2. Why is that? Remember, B tree is a layer of a linked list. So if the minimum is 1, then there can be an extreme case that the number of nodes in the upper level will be the same as the number of nodes in the lower level. If you set to minimum to get at least 2, this can be avoided. Of course, the situation I described is very rare, but in theory it can happen. But if you set the minimum to be 2, it will never happen. So maximum is 4 times the minimum. I think in the previous video I explained that the node is between a quarter full to full. So I choose to choose the upper level, the lower level to be a quarter full. And cutoff value to borrow or merge is 2 times minimum. If you set to 3 times minimum, that works too. And half is just the half of the capacity. Then you just instantiate the node. So you create a head node, and the zeroth index of the head node is the sentinel. And then the head node has one element, which is sentinel, so its length is set to 1. And initially there's only one node, so both tail and head points to that only node. Let's go to the search. Search is in this method. So this is the internal method, but in here, in the real B tree, so because this one is abstract data type. So for example, in the key value pairs, you call this method get leaf node. That's the same as this B tree of collections. So the real method is get leaf node. It's this one, get leaf node. So you pass in an index value you want to search. It will output whether you find the index, and you also output the index of the index of the index value passed in the leaf node. So you start from the root, then you do binary search in each node, then you go all the way to the leaf, and you do a final binary search at the leaf node. So this is the find index. That's the code for the binary search. There are some nuances you have to pay attention to. In case the node doesn't have predecessor, which means it's a head node in the linked list, you have to handle it specially. So basically, this is a binary search. When you find the index, you eventually do a comparison to see whether it's a search hit or it's a search miss. So the value of found is a boolean. If it's a search hit, then this is true. If it's search miss, then this is false. So this find index, this is pretty straightforward. So this is search. Then let's see to add. So this method is protected, but actually this is the method is doing the work. For others, they are actually, for the public method, it's just a wrapper of the this protected add method. So you add, you pass in a value, a key value pairs, basically a value of a key and a value. So from here you still you start from the root, and you use binary search to go to the leaf, and then when you add leaf, you do a final binary search to see whether the key exists or not. So if the key exists, it's there already, then you do an update. So you do an update. When you do update, you can see the deleted will have something that's the old value basically. So if you search hit, you're done. You do the update, and then if it's a search miss, you do the insertion. So do the insertion, you need to check whether the leaf node is full. If it's not full, then you have room to do the insertion. So this one is basically you shift the array, so you do the insertion. So the insertion should be I think should be after this index you found. So this one you just shift the array, you do the insertion, then you are done. What if it's equals max, which means it's full? When the leaf node is full, you have to split the leaf node. Remember, to split the leaf node, you actually create a new node and insert a new node after the existing leaf node. So this insertion is linked list insertion. So you return the new node you created. So this is the implementation of split leaf node. I think it's you create a new node, and then you because you have to insert a new element into the node. The element to be inserted may be in the new node, it may be in the previous node. So you just depends on where the index to be inserted, and then you return the new node is created. Then you have a new node. Then you propagate upwards. So you propagate from the new node's parent will be the same parent of the existing node. So basically, you propagate upwards means in the parent you have to insert new element of the new node. So you do the same thing. If the parent is not full, then you shift the array and do the insertion. Then you are done. You don't need to propagate upwards even more. What if the parent is also full? Well, you do the same thing, but you split the index nodes. You know, when you go to the parent, that's the index node. You split the index node. Then you actually have a new node of the index node. Then you do the loop again until either you have enough room to insert a new node, or you propagate all the way to the root. So here, when this loop finishes, when this loop is finished, then if the new node is still not null, which means you split the root. So in here, this is to create a new root. Basically, I think as I mentioned in the previous video, you have to create a new root, and the new root, the first the zeroth child of the new root is the old root, and the child at the index being 1 is the new node. So basically, this one you create a new root, and then you finish the insertion. So this is insertion, and let's go to deletion. So deletion, you pass in a key, and then you delete the element based on this key. Still, you start from the root. You go to the leaf, and the leaf you do a final binary search. And if you search miss, means the key doesn't exist. You don't need to do anything. Then you are done. If the it's a search hit, means the key exists, and then you do the deletion. In these two situations, is whether the B tree is a key value pairs, or is the B tree just a collection of comparables. So after you delete at the leaf node, of course you have to adjust its length. You reduce by 1. Then here the key, here the tricky part. You because the leaf node got shrinked, it may have fewer elements than the minimum. Then you call this method to see what kind of delete action you have to do. This returns the enum. Okay, the enum for the delete action, there are actually 5 types of actions. None means you do nothing after deletion, or you do merge with the sibling nodes, or you borrow from sibling nodes. So based on the I think here, based on the minimum and also the number of elements it contains, you find the delete action. So basically, this is the implementation. I think it's there's if this one, if it's a root, you do nothing. As I mentioned, the root is allowed to have less element than the minimum, and with greater than minimum or greater or equal to the minimum, you do nothing. But there is one exception, which means the deleted element is at 0 index. In this case, because the index at 0 serves as the index in the parent, so you have to update the parent. That's only one exception. And here, if the node contains sentinel, means it doesn't have predecessor, so you deal with the successor. And if the node has predecessor, which means it's not the head of the linked list, then you deal with its predecessor. I think I explained why you try to deal with the predecessor in the previous video. So you get the delete action. Then based on the delete action you found, you take the delete action. So this method is to take the delete action. So it's based on, let's see where here. Based on the delete action you found, what you do, if it's none, means you do nothing. And then if you borrow from the predecessor, in this case, you need to return the existing node, because the zeros index of the existing node is modified because it's borrowed from predecessor. If you borrow from the successor, it's only for the node containing sentinel. You return its successor, because the zeros index of the successor is modified. If you merge into its predecessor, means the existing node will be deleted, so you return the existing node. And if you merge from the successor, so you return the successor. This is the successor. It's the temporary pointer of the successor, because its successor is to be deleted further. So you take this action. So in here, you have this delete action and a node. You initialize these two variables. And here is a little tricky part. If the node to be deleted is the tail node, so you may have to reset the tail pointer for the linked list in the leaf level. And then here is what you do to propagate upwards. So to go upwards, you have the previous node. You go to its parent, and remember, each node stores its own index in its parent. So you have the index. Then, based on the delete action you found, you see how it propagates in the parent. If you borrow either from predecessor or borrow from the successor. Remember, when you borrow, you don't delete any existing node. You only update its index. So in this case, you update the index. If in general you don't need to propagate upwards, there's only one exception, means the index is 0. Then you have to go, you update its because 0 index is the index at 0 is the index in the parent. So you have to propagate even further. That's only exception. So when you do merge, so you deleted the node. So this node is deleted. So you have to delete this node in its parent, and then because you delete one element, so the length get reduced by 1. Because you delete one element in the parent, so you have to call this method again. Do you need to borrow from the parent's predecessor or successor, or do you have to merge the parent with its predecessor or successor? You have to call this method again. Then it's possible to propagate even further. And here is to propagate to the root. So what happens is if the root has only one child, and the root itself is not leaf, then you have to reconnect the root to its child at index 1. Then you reset the pointer, so it has a new root. In this case, the height will reduce by 1. And I think that's the deletion. There are a lot of helper methods. You can see these are the helper method. It's essentially mostly static method. You shift the array, you split the array, and there are a lot of nuances you have to pay attention to, but there's not much to explain. But one thing you have to pay attention is that when you split the node, or you merge the node, or you borrow element from node, if that happens in the index node, you have to adjust its children, because the children will have a new parent, and the children have new index. Not only for index node, but also for the I think that's essential for index node, because when you do something on the leaf node, so it has to be done in the upper level. So here is a method has key, so it's whether its key contains, for example, key value pairs. I think the C# dictionary, like the C# dictionary API. And lastly, this is the validation. This is not a part of the implementation. It's the test code I wrote to validate the B tree. Remember, B tree is just a layer of linked list. So I just verify the layers of linked list from left to right for each layers, and from right to left for each layers, and from bottom to root. You start from each node in the leaf level, so go upwards to the root, and this one is from root to the bottom. This one is basically level order traversal. So all the 4 files I have uploaded to the Google Drive, and the link is in the video description. Hopefully these 2 videos will help you understand what B-tree is and how B-tree works. Thank you for watching. Bye-bye.